I feel like we're in quarantine week 4, and my hair is at quarantine 6 months. Just keeps growing. It's because I'm lazy about cutting my hair, so, now it's gotten to the point. Actually, I have to tie it back. This doesn't look too bad. Anyway, yeah, so welcome back. I feel like we've been scrambling to get through like all this the last few weeks of the semester. And so I've been posting lesson after lesson after lesson talking about the definition of the Laplace transform. We talked about some special properties of the Laplace transform. We've talked about the invertibility of this Laplace transform and solving initial value problems with the Laplace transform. Some of those videos took about actually 2 videos in order to get them done. And so I still want to talk about the convolution theorem, and I think that's probably where I'm going to wrap up. With the exception of some special topics I'll do after my upcoming exam. But then after that, that'll be the Laplace transform, broadly speaking. There's some other topics that are in there, in the textbook they talk about Laplace transforms of periodic functions, and they talk about a couple of other discontinuous functions, talk about the gamma function, which I might put in one of the special topics, things that are good to know about. But as far as the actual solution excuse me, to Laplace transforms, I think we're covering the bulk of everything that we're going to want to do. Of course, I'm hit with hiccups right now. Anyway, yeah, so so that's good. So in response to try to slow things down a little bit, what I'm going to do is I'm going to just go over a bunch of homework problems from first here, section 7.2 and 7.3, and then after that we'll have another follow-up video, hopefully by the end of the week, covering 7.4 and was it 5? I lose track of things. Anyway, but right now it's 7.2 and 7.3, and we'll get to the other ones later. And then we'll have a few examples with the convolution theorem later. And and then that'll be prep for exam 3. Or for my class, exam 3. I mean, wherever everybody else in the world is doing, it's fine. So that's where we are. And let's go ahead and jump into it. Okay, so let's jump into this. So we're looking right now at section 7.2, and this is in Nagle, Saff, and Snider. I think it's 9th edition? Yeah, 9th edition. Anyway, if we take a look at, say, some of these problems, some of them actually aren't too different from what we've seen already. Let's take a look at, say, I'll do 3 problems from here, and we'll be good. So let's start off with problem number 4, where we have f of t is equal to t times e to the 3t. And what they want us to do is they want us to compute the Laplace transform. Let's say of f. All right. This one's going to end up being we're going to end up using integration by parts, and we're also going to combine this with the exponential inside the Laplace transform. So if we write capital F for our Laplace transform, then we have integral from 0 to infinity of f of t e to the 3t, and this is the definition of the Laplace transform. So expanding f, we're going to get this integral from 0 to infinity. We have t times e to the 3t e to the minus, oops, I'm sorry, that was just wrong. So that should be e to the minus st dt. That's the definition of Laplace transform. Brain fart. I saw this guy and got carried away. Anyway, so now we can expand f, integral from 0 to infinity of t times e to the 3t times e to the minus st dt. And we have the integral from 0 to infinity of t times, say, e to the 3 minus s t dt. Okay, so honestly, what we could do is we could even start with our properties if we were starting with 7.3. So if you're, and we could actually use the fact that we have shifting, which is exactly what we see here. So since we already know about shifting, we're keeping that in mind. But pretending we don't and just using the definition, because we're asked to use the definition, we're going to go ahead and do this the long way. So first of all, we need to change this to a limit of integrals, because it's an improper integral. So a limit as capital N goes to infinity of the integral from 0 to n of t e to the 3 minus s t dt. Okay, so that's going to give you now a limit as n goes to infinity of something. We need to do an integral here. So that's going to be integration by parts. So here I'm going to set u is equal to t, and I'm going to set dv is equal to e to the 3 minus st. Right? So that tells me that du is equal to dt, and that tells me that v is equal to e to 3 minus st divided by 3 minus s. All right. So let's multiply those together. So we get uv, so we get t times e to 3 minus st divided by 3 minus s. 3 minus s. And then minus the integral of v du. So that's going to be e to the 3 minus s t dt, and we can put the 3 minus s outside. Integral from 0 to n. And this needs to be evaluated at 0 to n. Okay, so if I go ahead and, well, let's just finish out the integral. Putting these off on the side, we get that the integral is equal to the limit as n goes to infinity of, well, now let's go ahead and expand this guy. So we're going to have n times e to the 3 minus s n divided by 3 minus s minus 0, because at 0, t is 0. Now we have minus 1 over 3 minus s, and we can integrate this last bit as e to the 3 minus s n divided by 3 minus s. Or not at n there yet, that should be t. Let's go ahead and erase that. So that's still t, and we're evaluating this at 0 and n. And we can go ahead and do that. So we can take this first bit and we can look at what happens so this is going to diverge unless s is bigger than 3. So we'll just assume that s is bigger than 3. And then what we're going to have then is that when s is bigger than 3, 3 minus s is negative. So say over inside, 3 minus s is negative, which means that this whole term goes to 0 as n goes to infinity. So we get limit as n goes to infinity. This is 0, this is 0, so those go away. And we're now left with 1 over 3 minus s squared, where this guy multiplies by this guy. And this is now multiplied by e to the 3 minus s n. And we already wrote down the other bit, so we wrote that down. Minus 1. Right. So now as n goes to infinity, oh, and we have this minus sign that needs to come and hang out somewhere, so I'll put that there. Okay, so as n goes to infinity, this goes to 0, right? We just showed that. And so all that's left is we have minus and a minus, and so then we're going to have 1 over 3 minus s squared. There we go. So that's not too bad. So now for fun, let's go ahead and take a look at what would have happened if we used our properties of the Laplace transform. So so number 4, but in the context of 7.3, right? So we're looking for a Laplace transform of t e to the 3t, Well, we know one thing is that if we have Laplace transform of e to the at times f, then this is the Laplace transform of f shifted to s minus a. And if I multiply by t times f of t, then this is minus the derivative respect s of Laplace transform of f of s. Right? So what are we going to start with? So I'm actually going to start with Laplace transform of 1. We know what that is. That is 1 over s. So now if I look at Laplace transform of now t, this should be minus the derivative respect to s of 1 over s, and that's going to give me 1 over s squared. Now if I take Laplace transform of t e to the at, and in this case not just a, it's 3t, then what is this going to give me? It's going to be 1 over s minus 3 squared. And there we go. Now if we take a look back here, we had 1 over 3 minus s squared, but since it is squared, this is actually the same as 1 over s minus 3. We'd be multiplying by a negative, but since it's squared, all negatives are changed to positive, so it doesn't matter what order those are in. So there we go. Here it's a lot faster to get to the end if we're just clever. So we started with Laplace transform of 1, and we built up to Laplace transform of t e to 3t. Okay, so if we asked to do it with just using the definition, then obviously go through and do the whole definition. If you're asked just to find it, say using 7.3, we can use it with the shifting and the derivative properties. And then, of course, this is actually on the table, so even then, it's easier than that. Okay, let's see. Let's grab another problem. So the other problems are like e to the t sine of 2t, e to 2t cosine of 3t, etc. So for instance, I'm not going to do this whole problem because it's going to take a long time, but I'll get you started. So let's say that we had f of t is equal to e to the 2t times cosine of 3t. Well, if we're going to do this using the definition, then we're looking at f of s is equal to the integral from 0 to infinity of, say, e to the 2t cosine of 3t, e to the minus st dt. And then we can combine things, and we have cosine of 3t times e to the minus s minus 2t dt. I just moved it in here because this really reflects the shifting property. But from here on, we have a cosine times an e to the t, so we're going to use integration by parts. And it's going to be used twice. And we're going to set u is equal to cosine of 3t, and we're going to set dv is equal to e to the minus s minus 2t. And then what that gives you is du is going to be equal to minus 3 sine of 3t, and v is going to be e to the minus s minus 2t divided by minus s minus 2. Right? And then you're going to be set up with this guy and this guy inside the integral multiplied together. Then you're going to basically set this dude as u the next time and do it again. And so this is going to be a solving for the integral. And this is going to work exactly the way that it worked in the example in the lecture. So so I'll leave you with there. And yeah, so we can stop on that one. Again, go back to the lecture, watch what I did there, and you can just emulate that exact process through this. And if you want to double check your answer, from 7.3 perspective, we can also use some of the properties we've already found. So for instance, we know that Laplace transform of f prime of t, for instance, of s, is equal to Laplace transform of f of t times s minus f of 0. Right? And then we also know, again, the e to the at times f of t at s is going to give us the Laplace transform of f shifted at s minus a. So we know that cosine. So we know that if we take the derivative with respect to t of sine of bt, that's going to be b cosine of bt, right? And we have the formula for this from the lecture. It's in our table. So the Laplace transform of sine of bt then of bt was found to be 1, or b rather, over s squared plus b squared. And now if I want to find a Laplace transform of cosine of bt, this is 1 over b times the Laplace transform of sine of bt. And so then we get s over s squared plus b squared. And then after that, we just need to do shifting. So we have the Laplace transform then of e to the 2t cosine of 3t. So b is 3. And we shift by 2. So s minus 2 divided by s minus 2 squared plus 3 squared, or 9. Okay, so that's ultimately what the answer would be after you do everything. So if you're asked to do this on the exam, I mean, obviously you're going to have to go and do solving for the integral if you're told to do it from the definition. Otherwise, you're free to use tables or using the properties of the Laplace transform. So ultimately, though, if you want to double check your answer, that's what you'll get. Okay. So for number 11, what do we get? We have f of t is equal to, it's a piecewise equation, so we have sine of t here, and we have 0 is less than t is less than pi, and then afterwards we just have 0 for pi less than t. Sorry, t bigger than pi. Okay, so we're going to try to compute the Laplace transform of f, so it's the integral from 0 to infinity of f of t e to the minus st dt. But we know now that we're 0 for all t bigger than pi, so it's actually 0 to pi of sine of t e to the minus st dt. Okay, so now we got to figure this one out. All right, so again, this is a problem where we need to solve for the integral, and we're going to use integration by parts. So here u is going to be equal to sine of t, and dv is equal to e to the minus st dt. And so then we get du is equal to cosine of t dt, and then that means that v is equal to e to the minus st divided by minus s. So throwing it all together, we get uv, so sine of t times e to the minus st divided by minus s, minus the integral of v du, so integral of e to the minus st divided by minus s, and du is cosine of t dt, and so it's got a plus sign there, and we're evaluating this at 0 and pi, and 0 and pi. Okay, so at 0, sine is 0, and at pi, sine is also 0. So this is actually equal to integral from 0 to pi. Mute that. So integral from 0 to pi of cosine of t e to the minus st dt. Okay. And 1 over s popped out. Okay, now we're not quite done. We need to do integration by parts again. And so here we're going to set u is equal to cosine of t, and that means that du is equal to minus sine of t. And then we're going to have dv, again, is e to the minus st dt. And then our v is, again, going to be e to the minus st divided by minus s. So we have 1 over s times, it looks like we're going to have uv, so cosine of t times e to the minus st divided by minus s, minus the integral of v to u. So we get, again, flipping the sign, integral from 0 to pi. 1 over s pops out again, is sine of t e to the minus st dt. Okay, great. And this is valued at 0 and pi too. All right, so we can go ahead and work that out. So we get 1 over s. Now cosine of pi is -1. So we get, say, e to the minus s pi divided by s, because I'm flipping the sign because of the cosine -1. And then we're subtracting off what we get when cosine is 0. We put t is 0, and so we get cosine is 1. E to the minus st is 1 when t is 0, and so we get 1 over s and flipping the sign. Okay, so now we get plus 1 over s integral from 0 to pi of sine of t e to the minus st dt. All right, so let's just go ahead and call this our integral I, and on the other side, that's what we had here. We had our integral I. So ultimately we have this equation. We have I is equal to 1 over s e to the minus s pi divided by s plus 1 over s plus 1 over s I. All right, let's move things around, distribute the 1 over s. So we get 1 over s squared plus 1 over s squared plus 1 over s squared times I. All right, and now if I move the i's over, I get 1 over 1 minus s squared times I is equal to e to the minus s pi divided by s squared plus 1 over s squared. And then that tells me that I, which was the integral from, well, which was really f of s, is going to be, let's see, it's going to be 1 minus 1 over s squared, and taking reciprocal, e to the minus s pi plus 1 divided by s squared. If you do some further computations, it's going to be, we're going to have s squared divided by s squared minus 1 times e to the minus s pi plus 1 divided by s squared, and then that gives us is f of s is equal to e to the minus s pi plus 1 divided by s squared minus 1. And there you go. Okay, so there we had to do a little bit of solving for the integral. Okay, so let's take a look at some of the other problems. So a lot of the problems, say 21 through 28, they're just asking us to determine whether f is continuous or piecewise continuous or neither on the interval 0 to 10. So that's a definition thing. I just go ahead and look at it and determine it for yourself. For me personally, I'm not going to ask that sort of question on the exam, or well, maybe I will. I don't know. But yeah, and let's see. Okay, so problems 13 through 20, they ask us to use the Laplace transform table and linearity of the Laplace transform to determine the following. So basically what we're going to do is we're going to take, this is really straightforward, I'll just do number 17 here. So what we have is we have the Laplace transform of e to the 3t cosine, sine of 6t, minus t cubed plus e to the t. And so all we're going to do is just take a look at our Laplace transform table. So for instance, we already talked about, say, what Laplace transform of e to 3t sine, or say e to the at sine of bt is s, that's going to be b over s minus a squared plus b squared, right? So that's 1. We have the Laplace transform of t cubed. We know is going to be 3 factorial divided by s to the 4, if I remember right. And Laplace transform of e to the at is 1 over s minus a. So, so we're just going to basically use these guys that come straight from the table. And this is table 7.1 on page 356. And let me just double check one thing. Yep, right on all accounts. Okay, so let's go ahead and do it. So the idea is that we can actually split this guy over the sum, and we can pull out constants, right? So we get Laplace transform. This is equal to the Laplace transform of e to the 3t sine of bt minus the Laplace transform of t cubed, and then plus the Laplace transform of e to the t. All right, and so then Laplace transform of e to the 3t sine of bt, that is or sine of 6t. Sorry. So that's going to be 6 divided by s minus 3 squared plus 36, right? And now we get minus, well, we have this written explicitly, 3 factorial, about nearly that, as 6 is 3 factorial, over s to the 4, and then we have plus 1 over s minus 1, and we're done, right? And so that's all the problems in that little chunk. Just keep referring back to the table, and you're done. All right, so that's section 7.2. All right, now section 7.3 is, again, we're going to be determining the Laplace transform of tables, of the functions using the table of Laplace transforms and also the special properties. And so this is, say, problems 1 through 20 here. And then, and if you even look at number 21, we actually already talked about that previously. So I've already kind of previewed this as we were going through the problems in 7.2, so there's not a whole lot new here. But why don't we go ahead and just talk about some of them. Okay, so here's a really good one. Problem number 9. Problem number 9 is, they give us f of t is equal to e to the minus t times t sine of 2t. So what I can do is I can actually start with something we already know. So on the Laplace transform table 7.1 that they gave us, we have that e to the at times sine of bt is equal to b over s minus a squared plus b squared, right? And we also know that Laplace transform of t times f of t, that is horrible, f of t is equal to minus d by ds of the Laplace transform of f. All right, so we're going to use this, and we're just going to use these two properties in order to figure out Laplace transform of this. By the way, I'm really sorry for my handwriting here. Although right now, honestly, is better than what it has been, because before I was on sort of a janky table that would sort of wiggle all over the place as I was writing. Now I've set up my proper desk since I actually have to work from home now. So hopefully my handwriting is a little bit better. I had my family actually taking jabs at me when they looked at my video. Anyway, so let's take a look. So we have Laplace transform of e to the minus t sine of 2t, right? And so this is just taking that t out basically tells us that we have minus the derivative with respect to s of Laplace transform of e to the minus t sine of 2t. And now we just need to take the derivative of that. So what is that? Well, we know that we can replace this guy with this guy here. And so now we're left with 2 divided by s minus, or negative 1, so it's going to be plus 1 squared, and then plus 4. All right, Now if I take the derivative of that, let's see. So we can just go ahead and use chain rule because this can be written as 2 times s plus 1 squared plus 4 to the negative 1. And so then what we get is we get minus 2 times, we get negative 1 times s plus 1 squared plus 4 to the negative 2, and then this times the derivative of the inside, which is 2s plus 1, right? And so altogether we get, so we have, say, 4s plus 1 divided by s plus 1 squared plus 4, and that quantity squared, right? And that's the answer. All right, let me do one more problem, and then we'll call it a day. Let's see. Here's an interesting one. Number 13. Here, we have sine squared of t is f, right? All right, so now we want to use the properties of the Laplace transform in order to figure out what that's going to be. What would I do? Well, probably the best route to go here is just to go ahead and use the half-angle formula. So sine squared of t can be written as 1/2 of 1 minus cosine of 2t. I always double check that, because if I put in 0 here, I get 0, and so then that matches up with sine squared, sine of t being 0. So using the half-angle formula, that gives me that, and then taking a Laplace transform of, say, sine squared of t is going to give me then 1/2 Laplace transform of 1 minus 1/2 Laplace transform of cosine of 2t. All right, so here all we're doing is we're exploiting linearity. And so then we get 1/2 of 1 over s minus 1/2 of the Laplace transform of cosine of 2t. So if you remember, Laplace transform of cosine of bt is equal to s over s squared plus b squared. And so now that's going to give me s over s squared plus 4, and we're done. If you want, you can keep combining terms, so we can say it's 1/2 times s squared plus 4 minus say s squared divided by s times s squared plus 4, just combining fractions, and so then we get nice and clean. S squared cancels s squared, and then 4 divided by 2, and so it's 2 over s times s squared plus 4. Right, there we go. So that's not too bad. Honestly, that went way too fast. Let's see. Yeah, so all that uses linearity. These really aren't all that complicated. So for instance, there's another one in here, say number 11 is cosh of t, or cosh of bt, so he wants to be general. But cosh is really just e to the bt plus e to the minus bt divided by 2. So then you just use linearity. Hell, I can even write it right now. So Laplace transform of cosh of bt is equal to 1/2 of 1 over s minus b plus 1/2 of 1 over s plus b. And so then we can pull out the 1/2, and we multiply this guy top and bottom by s plus b, this guy top and bottom by s minus b, and so then we get 2s divided by s squared minus b squared, and ultimately what we get then is s over s squared minus b squared, right? so not too bad. Okay. Okay, so yeah, I think this is where I'm going to stop for today. It covers enough examples from 7.2 and 7.3, so you get the idea of how to navigate around the Laplace transform using special properties and using the tables. And my kids are home and screaming in the background, so I think that's where I'm going to have to end it today. All right. Okay, so hopefully everybody feels a little bit more prepared for handling problems in the Laplace transform. 7.2, a lot of that is just remembering how to do indefinite integrals. And 7.3 is about using the tables that we have from section 7.2 and 7.3 in order to do some quick manipulations to get Laplace transforms. So you can really build up everything, like I said before in the lecture, from just one or two integrals that you did in the Laplace transform definition section, and then after that you can use simply the special properties. So anyway, yeah. So with that, I think I'm gonna end today's lecture, and yeah, I'll see you next time. Good luck with your study.